In the sticking collision scenario, the most basic example is train cars. A train car moving forward at some initial velocity collides with another train car, in this particular case not moving, but could totally be moving in either direction. Due to the mechanical systems of the train, when they hit together, they combine and become not train cars, but instead a train moving at some new speed, which would generally be the unknown characteristic. When we look at it through conservation of momentum, again, we are defining the momentum of the system equal to the momentum of the system afterwards, right? So we are closing off the system and isolating two particular parts and defining the momentums as being conservative within that closed system. So we have, again, momentum 1 plus momentum 2 equal to momentum 1 prime plus momentum 2 prime. It looks very similar to the bouncing case, and in all thoughts and setups, it basically is. The one key point here is to make sure we understand a few characteristics about this side that set them apart. We know that when they combine, V1 prime is the same as V2 prime because they are connected. So by definition, we can redefine these as just V3 prime. And that's extremely useful for the setup for the generic equation. So when I define or I substitute in what I know about momentums for each one of these, I end up with m1 v1 plus m2 v2, the motion of the two carts and their individual masses before they collide, applying a frame of reference on each one of these, obviously, for the vectors of the velocities. But then on the other side, I know that m1 and v1 prime are going to add to m2 v2 prime. But then what we're going to do is we're going to use this here and substitute in v3 for both v1 prime and v2 prime to get a more clean and more defined sticking equation. So I have m1 v1 repeated plus m2 v2 before the collision, but then afterwards I have m1 times v3 plus m2 times v3, v3 being after the collision in this case. So obviously v3 is common to both terms, and so now if I write m1 v1 plus m2 v2, we see that on this side the masses add, m2, and they are multiplied by v3 prime. So this is your basic generic equation for sticking, where two objects become one object. Now I could go ahead and substitute and call m1 plus m2 m3, but generally we are not going to know the total mass of the object. We are instead going to know mass 1 and mass 2. So we're just defining this as a way of identifying that these things are sticking together. But again, this is a specific case to this particular example, which is why we don't generally start with these generic equations. It's not unreasonable to think that this could be reversed, where this becomes the initial term and these become the after term. The most common example is a cannon problem, where we have a cannon with a cannonball down inside. Obviously you could not see that the way the cannon is set up, but sitting on wheels launching the cannon. And so here the momentum of this system is not moving, but moreover it is two objects combined together on this side. So I have m1 plus m2 times v3, but then upon firing, the cannon here recoils backwards as the cannonball moves forward, right? And so we end up with a sticking reversed, where I have m1 v1 prime plus m2 v2 prime, right? And so basically what I've done is worked backwards. And so if we had started at the top, we would have started with P of the system equal to P of the system prime. and then just gone down through and identified this side as being this combined side with the common velocity term, and then this side as the separated out pieces. This is why I find it valuable to just start with this statement always and not always hold to this generic equation, because it won't always match up to the scenario.